Remember that Cartesian coordinate system? We were looking at the Cartesian coordinate system. So I'm going to share my screen here, share my .cam, and just sort of take us through a little bit of what we did last time and bring us back up to speed. So we were in section 1.2. We talked about René Descartes and setting up this Cartesian coordinate system. And we said that, hey, there are axes in this coordinate system. We have the X and the Y axes. We have ordered pairs depending on how far we go right and left and up and down. Those are X and Y. And we have this separated into 4 parts. They're called quadrants. So we start with quadrant 1 over here at the right-hand part. And we go counterclockwise to quadrant 2, 3, and 4. And they're conveniently written in Roman numerals because no one uses those anymore. No, Super Bowl, right? I think the Chiefs were like Super Bowl X1V. They won that one. Or no, wait, L1V, sorry. L is 50. So, you know, Roman numerals there that we use. And then we have this special point in the middle, 0, 0. Now, we talked about how to find the equation of a circle last time. And it's really based on this Pythagorean theorem, or we can generalize that to what we call the distance formula. So if I want to find the distance between any 2 points in this Cartesian coordinate system, you know, if they're on the same axis, so if I wanted to find the distance between this point and this point, that'd be pretty easy, right? I would just say it's whatever X is at this point and this point, whatever Y is. But if I'm trying to find something on the diagonal, that's not going to be so easy to find. So I can use this distance formula, and what it says, this should be sort of familiar to you, but the distance formula says that the distance between any 2 points and we just in general call them x1, y1, that's the first point, and x2, y2, that's the second point, is given by d is equal to the square root of the difference in the x's squared and the difference in the y's squared. And I just, for some reason, wrote that as x1 minus x2 squared plus y1 minus y2 squared. Probably in the textbook, it would have been the other way around. It doesn't really matter because when you look at the distance between these 2 points, we square it. And so if this was negative, we square it, we still get a positive answer there. So the distance between any 2 points is given by this formula. So for instance, if I wanted to find, let's say the distance between the point 0, comma, -1, oh, that's a special point, right? It's on the axis. What do they call that? That special point that's on the y-axis?
It's an intercept.
Yeah, great, a y-intercept. Thanks. Thank you, Laura. And then let's say that we have another point over here. Let's call it, let's not put this one on the axis. That might be a little bit too easy. Let's put this one down at, let's say, 5, -3. Okay, so if I wanted to find the distance between these 2 points, I could plug it in my formula. However, where does that formula come from? It comes from the Pythagorean theorem. So if I sort of connected these 2 points and made a right triangle, what is the x distance between these 2 points? Who can tell me? The x distance.
5.
5, great, Connor. So I would take 5 minus 0. I look at the difference between the x's, and this is 5. Now, what's the distance in the y value? Anybody?
2.
Yeah, thank you. I think that was cool. So -3 minus a -1. So the distance, we just subtract the y values, and that gives us a -2. We know the distance is positive. So when we plug these things in the Pythagorean theorem, we would get 5 minus 0 squared, that's 5 squared, plus -3 minus a -1 squared. And that's not equal to the whole distance, but it's equal to the square of the distance, right? So how do we find the distance? We just take a square root. And now you're going to see that that's exactly like the formula we have down here. So this would be 5 squared plus -2 squared square root. And again, we could do plus or minus, but distance is always positive. So we just do the +1. And it turns out that that one's going to be the square root of 25 plus 4, which is the square root of 29. So I couldn't just look at that and say, whoa, that's square root of 29 units. That's the distance between the two, right? So that's where this Pythagorean theorem will help us, okay? In the distance formula. So I wanted to bring that up because that's actually how we found the equation of that circle. If we remember last time, that circle with the radius of whatever, we would say, okay, we could use a distance formula. We could say, all right, x minus the x coordinate 0 squared plus y minus the y coordinate of 0 squared is equal to that radius squared. And bingo, here we have a circle centered at the origin. Okay. And whatever that radius is. So we sort of talked about that last time. Questions there on the distance formula? Okay. All right. Next thing we want to talk about it, right? And this is really important, so I'm going to put a star by it. Angles in standard position. So what does it mean for an angle to be in standard position? It means that an angle is in standard position like this one here. This angle theta is in standard position. Angles are in standard position if the initial side is, I should probably slide this up, boop, is on the positive x-axis and the terminal side can be either way. Is elsewhere. But if we go counterclockwise, the angle is positive. Okay. So let me see where I'm at here. I'm okay. All right. So what that means is, like this angle theta up here, it's not only in standard position, but it's also going to be a positive angle because this angle here, theta, starts out with initial side on the positive x-axis and it sweeps to this side here. I could extend that if I wanted to. This should show an angle. So this angle would be in standard position. And we know that angles that rotate counterclockwise are positive. If it does go clockwise, we could call it a negative angle. So standard position, we always start here on the positive x-axis. Sound good? Okay. Next, quadrantal angles. So this one, here's some more terminology. So this angle here, what quadrant does it terminate in? The terminator. What quadrant does this one terminate in? Anybody?
First quadrant.
Yeah, quadrant 1, great. Sometimes we have notation for that. We would say, okay, so this angle theta, you'll see it in the textbook and we'll use it a lot. Theta is an element. So this is like an E, is an element of quadrant 1. That means that theta terminates in quadrant 1. Okay, but some angles don't terminate in any quadrant. They terminate on the axes. So we call these quadrantal angles that terminate on the axes. So these are angles in standard position. Which terminate on an axis, either the X or Y axis. So can anybody give me an example of a quadrantal angle? Maybe their favorite one, or maybe one they don't like so much.
270.
Awesome, Grace. So 270 is a great example of a quadrantal angle. That's sort of hard for me to say. Boy, I lost it there. All right, so nice job, Grace. So this one goes all the way around and terminates down here on the negative y-axis. Great. Who wants to give me another one? It can be one that you like really a lot, or maybe one that's done you wrong. Maybe one you're ambivalent
90.
about. 90. Okay, that's a good one. I like that one. That's one of my favorite quadrantal angles. All right, so that one goes and hits the positive y-axis. Right. Okay. So these are some great examples of quadrantal angles. Okay. One more piece of terminology, and then we'll get to some more math here. So we have things called coterminal angles, and coterminal angles are important because they start at the same place and they terminate at the same place, but they're not the same angle. Okay. So coterminal angles, we can say that they're angles in standard position. So they're all going to start on the positive x-axis, which share a terminal side. So they have the same terminal side, but are unequal. They're unequal. So if your imagination is running wild now, like I could say, oh, okay, what about that 270-degree angle that Grace gave me, that quadrantal angle? I could say, well, this angle is coterminal to it. This one's going clockwise, and this one would be negative 90 degrees. Or I could say, hey, maybe I want to spin around twice. And I could get there again. So that one would be over 360 degrees. So 360 plus 270. Oh, no. 360, 540, 630, 720, 630. 630. Okay. So you can create a whole bunch of coterminal angles, but they're going to be important because they are pretty much, when we discuss the trig functions, which will be soon, we'll get pretty much the same answers when we compute those. All right, any other questions before we get into some examples? Okay, let's look then. So I need to probably slide this up. I want to find the point on a circle. X squared plus y squared is equal to 25, which is on the terminal side of a 135-degree angle in standard position. So the first thing I need to know is what quadrant is that angle in? So theta is in which quadrant now? Who can help me out? 135-degree angle.
Quadrant 2.
Exactly. Thank you. So this angle theta is going to be in quadrant 2. We want to find the point on the circle that has x squared plus y squared is equal to 25. And you might know that that's a circle that's centered at the origin, a radius of, what's the radius of the circle?
5.
Yeah, 5. Okay. So I'm going to show you what we were doing yesterday. Let's see, because I think that I can just sort of tap into this. Let's see. Okay. Boom. Okay, so do you see my Desmos circle there that we were looking at yesterday? Great. All right. So really what we're looking at here is we're trying to find, we've got this angle that's going to terminate over here in quadrant 2. It's a 135-degree angle. So it looks something like that. And we want to find where that angle intersects with the circle of radius 5. So we need to find the x and y coordinates of this point. So one thing we can do is if we have angles that are over 90 degrees, sometimes what we're going to do is we're going to sort of look at those, breaking this into a triangle, but we like to work with acute triangles. So we use an angle that actually is going to be with the x-axis. So I'm going to sort of write down a triangle for you that I think would be wise to use. So here we have this triangle, this pink triangle, which is butting up to the x-axis. So we know that this is a right triangle. And what are the angles for this right triangle here?
$45.
How'd you get 45?
I don't know. Just seems like that's what it'd be.
It just seems right. Okay. You're right, Jay. Nice job. So what we can do is, since we know it's 180 degrees around to that straight angle, we can subtract that 135 from the 180, and that will give you the 45-degree triangle. Nice. Okay. And that's what we're going to do. So these actually have a special name. When two angles add up to 180, they have a name. Anybody know what the name of it is? You might have seen it in the homework. So two angles that add to 90, we knew were complementary. Two angles which add to
supplementary.
Yeah, very good. To 180 degrees are supplementary. I think that somebody told me, I think it was one of the videos actually, that complementary C is in the alphabet before S. So C is the one that goes to 90 and S is the one later that goes to 180. I don't know. However you memorize it, that's cool. So we have a supplementary angles there, 135 and 45. We use these supplements quite a bit because we know how to work with acute triangles. So this is a 45, 45, 90. We sort of talked about this before. We might know the ratio of those sides, but when we're looking at that, that triangle there, do we have a side that's given to us?
No.
Okay, Cam.
Well,
okay.
the hypotenuse is it's 5.
Okay, is that what you were going to say, Cameron? Nice. Okay. Yeah, I saw you shaking your head no, but then you had a second thought, and Cameron was over here. Oh, I know it. Yeah. So we do have one. Good. So you got there. That hypotenuse is going to be 5. So really, what we need to know are these x and y, coordinates. We could use something like the Pythagorean theorem. However, this is a special triangle, right? It's a 45, 45, 90. So what are the ratios of the sides of a 45, 45, 90, everybody?
I think it's a 1, 1, and 2.
1, 1, and you're so close.
Square root of 2.
There you go. Nice job, Cheng. Okay, so we have 1, 1, and root 2. Excellent. And so we're given the biggest side, right? We're given 5. So 5 corresponds with root 2. So what are the other two sides?
X.
Okay. And so now we can say x, and square root of 2 times x. So what is the x? In this case, when x is 5, we would have blank, blank, and 5. but that's the right way to do it.
2.5 square root 5.
There you go. 2.5 square root of, not 5, but
Square root 2.
there you go. So 5 halves square root 2. So each one of these are going to be 5 halves square roots 2. Or, you know, if you want to think of it this way, since 5 is to root 2, to go back to get 1, I would divide by root 2. I would divide by root 2. So I take this 5 and I divide it by root 2. So 5 over root 2 would be the correct answer. Also, 5 over 2, square root of 2 would be a simplified answer. So if I went ahead and multiplied by root 2 and root 2 here, root 2 times root 2 is 2, I would get this answer that you told me, okay? So either one of those would be okay. However, we know that x goes left, so the x1 is negative, right? So this x1 is going to be 5, -5 over root 2, or -5 over 2 root 2. And then the y is going to be +5 over root 2 because it goes up. Look good? Whoa. Questions there? So
Would
go ahead.
would giving you a decimal answer for a question like this be incorrect on the homework?
It might be on WebAssign. I'm not sure. Maybe you might want to try. I would count it correct on a test. Okay. It's not really standard notation to take a decimal times the square root. Usually it's more of a fraction times the square root. So you could give it a try. I think WebAssign gives you like at least 2 or 3 tries to get it.
Set to 5.
Okay.
I looked.
5. Great.
It would say like you have used this many of 5.
Okay. Wow, I'm generous. That's good. But I want you to learn from the homework. Okay, great. So you get 5 tries. So take one of those tries and see if it works. If it does, then you can keep doing it that way. I'm cool with it. Okay. Good question. Any other questions there? Now, one thing you might have noticed is that this circle is going to have a lot of symmetry. So even like when I look at something over here, this is going to be the point I have here. That's 5 over root 2, 5 over root 2. So what that means is, hey, this is going to be that 45-degree angle here. And the only difference between these are that they're approximations, but the first one's positive now. So the nice thing is if we can find the values in that first quadrant, then they're going to be the same in all the other quadrants up to a plus or minus sign. And I'm going to start saying SIGN because we're going to be looking at sign later. But yeah, you want to see the symmetry there with those triangles. Okay, great. All right. Whoa, stop share. Boom. Okay. A couple others here. So this is sort of like the speed round, maybe. I don't know. Let's see. Coterminal angles. So we found the answer to this one. I want to know 2 angles that are coterminal to that 135-degree angle. So we were just looking at 135-degree angles. Can somebody give me one and somebody give me another one? You can blurt it out or type it in chat with degrees.
-225.
Okay, that's a good one. So Grace decided to go negative on me. All right, that's good. So -225 is coterminal. Perfect. Starts at the same place, ends in the same place, but they're different angles. What about another one?
495 degrees.
495 degrees. Exactly. So you went around twice. or went around once and then a little bit more. Great, so 495 would work. If you went around twice, you would just add on 360, right? Or you could take Grace's angle and subtract 360, and you're gonna get all sorts of other coterminal angles. Awesome. Okay, last one. So we're gonna draw an angle of -30 in standard position. Okay. By the way, what quadrant would we be in when we draw this angle of -30? What do you think? I'm going to start calling them people, if you don't mind. What do you think, Logan? What quadrant would we be in if we had an angle of -30 in standard position?
Quadrant 4.
Quadrant what?
4.
4, exactly. Nice job, Logan. So we're going to be in quadrant 4. Excellent. That was sort of difficult because I gave you one that was negative, but Logan was not fooled. So this one, nice job, is in quadrant 4. So it might look like that in the textbook. So let's have an angle that's in quadrant 4. And I have a point on the terminal side that is going to be a comma -1. Okay, so if I extend this x over here, I can drop down a triangle and a and -1. So it looks like I go over a in the x direction. I go down 1 in the y direction, and I want to find the value of a. So you might remember this as a nice triangle. What's the other angle of this triangle? So if this is 30 over here, what's the other angle, Cameron?
60.
60. And Cameron, do you know what the ratio of a 30, 60, 90 triangle is in?
1 square root 3, 2.
That's it, right on the nose, man. Very good. So when we have a 30, 60, 90 triangle, the longest side, the hypotenuse, is always going to be twice as big as the shortest side, and that middle side is going to be √3 times whatever the shortest side is. Okay, so we do have one side of this triangle. It's across from the 30-degree angle, so it's actually 1. This one might be a little easy. So I'm going to put 1 here that goes with the 30. Okay, so what is A going to be? A is across from which angle? Caleb. A is across from the
60-degree angle.
It is. And so if this is 1, what is the one across from the 60? 1 lines up with 1, so we have what lining up with that?
Would it be negative radical 3?
Okay. So let's think about this. Our A is going to be over here, so it's going to be our X. So is our X going to the right or the left? Right is positive, left is negative.
Okay, so it's just radical 3.
There you go. Great job. Nice job, Caleb. So we're going to the right one. So this is going to be plus square root of 3. All right. So we can always, if we can find one side of a 30, 60, 90 or 45, 45, 90, then we should be in good shape to find the rest of them. Okay. Questions? Okay. All right. So now we're going to go into section 1.3, and we're going to be talking about how to find the trig function. So this is sort of, important, right? So I'm going to share something that's actually in your Canvas with you. Let's see here. And again, there are a lot of these helpful things. This one's going to be on the definitions of the trig functions. So let me start from the current slide, maybe. Oh, there we go. Okay, so we can define these trig functions by an angle and standard position. So you see my angle and standard position there. It's common to call these sides of the right triangle with reference to that standard angle. So the one that's closest, the side that is closest to that angle is called the adjacent side. So this adjacent side, it's closest to that angle, is going to be the adjacent side, or we can call it X. The side opposite the angle is going to be the opposite side, which we call Y. And then of course, the longest side is always the hypotenuse. Now, if you've heard anything about trig or the trig functions, or have had a course with any trig in it, you might have heard of this mnemonic, SOHCAHTOA, SOHCAHTOA. There will be a lot of things that we sort of have to memorize in this class. SOHCAHTOA helps because it actually defines the trig functions based on those sides. So S is going to stand for sine, and sine is going to be the opposite over the hypotenuse, so y over r. Cosine is going to be the adjacent x over the hypotenuse r, and tangent t is going to be the opposite side y over the adjacent side x. So this is how we define the trig functions. Notice that we abbreviate these trig functions. So I'm going to write the actual names of them there, if I can. Yeah, you can do a text. Oh, I don't like that. Okay. So this is called cosine. This is called sine, and it's abbreviated by SIN. So cosine is abbreviated by cos. And this is called tangent, and it's abbreviated by tan. Notice one thing that we need is we need these functions. They can't be alone, okay? They have to be acting on something, and that's the angle. So the input of these trig functions are an angle, and that's going to be that angle in standard form. So just like in college algebra or wherever you learned about log, you can't have log just by itself. You had to have log of x. Here we have to have cosine of something, sine of something, blah, blah, blah. Okay. And these are sort of the alternate trig functions, but they're important too. So I'm going to try to move myself over here without muting me. Okay. This SEC is called secant. This CSC is called cosecant. And this is called cotangent. Hot. So the good thing is if you can remember cosine, sine, and tangent as ca, adjacent over hypotenuse, so opposite over hypotenuse, toa, tangent is opposite over adjacent, then these functions over here are just the reciprocals of them. So if I can find cosine, I can find secant by just flipping, by taking the reciprocal. If I can find sine, I can find cosecant by taking the reciprocal. And tangent, cotangent. Cotangent and tangent, they seem to match up, right? That's sort of logical. The other ones might not be so logical. So the way that I sort of memorize it is that you have to have an S and a C. So if I have sine, its reciprocal is cosecant. If I have cosine, its reciprocal is secant. Whatever it takes to memorize these things, okay? So these are how we define the trig functions of these angles. And we're gonna be doing this with triangles first, but of course, as you go along to your next classes like calculus and things, we're gonna want to be looking at these in terms of functions, and we will be transitioning over to that in like chapter 4 or so. So we'll define them with triangles first, and then we're going to, it might help you to just keep this in mind. We're going to be transitioning these over to functions later. Okay. So let's look at an example here. unless there are questions. Sometimes I need to stop, right? Questions? Okay, everybody looks pretty chill. All right, so let's, I'm gonna clear this out and we'll go on. Let's look at an example here. Okay. Okay. So this might seem familiar. Let's have the adjacent side of a right triangle be 10 and the opposite side being 12. And we have that angle theta. We can think of it in standard position. We want to find all the trig functions of that given angle theta. Hey, you might remember from last time, we found that hypotenuse, it was like 2 root 61. Yeah. So it's the square root of 244. We used the Pythagorean theorem and we pulled out that square root of 4 as a 2. So now that we have all those sides, we can find the trig functions of those. So there's our triangle. And we see that cosine would be adjacent. So the one next to it, 10 over hypotenuse. So 10 over 2 root 61. And notice that I cancel out the 10 and the 2. So I do cancel out whole numbers that can be canceled out. But I will allow you to leave it unsimplified. So 5 over root 61 is an answer. But if you are a purist and you like to get those radicals out of the denominator, then good for you. I think that that's sort of more sexy, but I don't know. I get torn between sexy and lazy, and sometimes I just go for lazy, but those two would be the same thing. Okay. Sine, so okay, opposite over hypotenuse. So 12 over 2 root 61. The 12 and the 2 cancel to give me 6. That's the answer here. Tangent, TOA. So opposite over adjacent. 12 over 10 reduces to 6/5. And if I look over at my functions over here, secant goes with cosine. There can only be one S and C. So I just reciprocate this, square root of 61 over 5. Cosecant, I just take the reciprocal, square root of 61 over 6, and cotangent, I just get the reciprocal, which is 5 over 6. Sound good? Are there questions? So you're going to do this in just a minute. Before I have you go crazy here with it, I think I would be remiss if I didn't show you that, you know, when you have these angles that are similar, like if I had this theta here, and if I had this exact same triangle over here, all my trig functions would be the same, except for some of them would be negative now. So this would be a 12 and actually a negative 10 and a negative 12. And this would, the hypotenuse is always, it's always positive. So there's a little mnemonic that, another little mnemonic I use to figure out which is plus or minus. So it's called all students take calculus. If you can remember all students take calculus, then you can find a trig function in quadrant 1 and make sure it's going to be the same sign in the other ones. So what am I talking about with all students take calculus? If you're in quadrant 1, that means all of the trig functions are positive. So all of these trig functions are positive over here. If you're in quadrant 2, students, over here, only the y value is positive. So here, the sine of theta is going to be positive only. And of course, you know, it's reciprocal, so cosecant will be too. But sine over here is positive. If you're down in quadrant 3, take the ratio of 2 negatives, the positive, so tangent's going to be the only one that's positive over here. And of course, cotangent. And then in quadrant 4, calculus, all students take calculus. In quadrant 4, the cosine. That cosine is going to be the one that's positive. And of course, secant, but everything else is going to be negative. Okay, so that's a good way to see, if you've got the values in one quadrant, they're going to be the same in all the other ones, except for one might be negative. All right, so I'm ready to give you guys a shot at this. So I learned something by taking classes. Wow, that's a statement, isn't it? I learned something from taking classes, and that is that you guys can actually write on the screen. So you have to go up to where it says Chris M is sharing your screen, and you have to click annotate, but you should be able to draw on the screen. Don't do it yet, please. But I'm gonna have you do it in a minute. So now it's your turn. So this is the other triangle we were talking about. Your computer doesn't have that option? Really? It worked this morning. So click on my name and see if it doesn't say annotate. On the green Chris M screen. And if it doesn't, that's okay. We'll check it out. Oh, so it's not a feature on Chromebook. Bummer. All right. Well, that's okay. We'll get there. So we have this angle here. It's theta, and we want to find all the trig functions of this angle theta. Last time you used the Pythagorean theorem to find y, and you said 12 squared plus y squared is 13 squared, and you got y was equal to 5. So I want you, I want you to try to find all the trig values of this angle theta. And if you can just go in and put your answers in here. So go ahead and give it a try. If not, you could put it in chat, but you need to sort of see which angle this corresponds to. And you might have to make the color something that's going to show up here. Okay. So now feel free to draw away. You can even type if you want. Okay, so Connor says that sine is 13 over 12. Okay, Cole says that cosine is 12 over 13. And so cosine is right. If we know that cosine's right, somebody can jump all over secant right now, right? Tangent is 5 over 12. That's right. Very good. Now notice that 13/12 is the reciprocal of 12/13. So that's not going to totally be sine. Good job with cotangent. Okay. All right, I'm getting something in the chat. Secant of theta is 3 over 12. (13 over 12). Okay, yes, you're right. All right, Sean says sine is 5 over 13. Excellent. And then cosecant would have to be 13 over 5. Yay! We got it. Okay, so cosine. So good. It's going to be adjacent over hypotenuse, 12/13. So secant has to be the reciprocal. Sine, opposite over hypotenuse. So cosecant has to be the reciprocal. Tangent, opposite over adjacent. So cotangent is the reciprocal, and those are all great. So You guys are all stars. Okay. All right. Questions there? Nice. All right. Let me see. Sometimes I get carried away and see what time it is. So yeah, we're doing pretty good on time. I want to make sure that we hit most of the good stuff at least. Okay. Let's do one more example and then we'll hit up our last section today. Very nice. Okay, last example out of this section. Sorry about jumping around so much. I would just like if we could have a discussion, but I guess I teach in math, so it's more like examples than Spanish discussion or whatever. I don't know. All right, so here we have thetas in standard position, and we have the point -6, sorry, is on the terminal side. So let's see, Jacob, where does that angle terminate? If it's in standard position and the terminal side has the point -6, -6. So theta is in quadrant blank.
3.
Excellent. Nice job. Thank you. So here's our angle. And over here, somewhere at -6, -6, is going to be where our angle terminates. We want to find all 6 trig functions of this angle here. So if this is -6 and -6, we probably know the hypotenuse. Anybody want to take a venture? We could use the Pythagorean theorem, but we might know, since those sides are the same and it's a right triangle.
6 square root 2.
Yeah, it's a 45, 45, 90. Way to be on there, Connor. So this one's going to be 6 square root of 2. Now you could have used the Pythagorean theorem, but this is 45, 45, 90. We are in quadrant 3. So if we have -6, -6, then we would have some sort of 6 root 2 because these are in ratio of 1 to 1 to root 2. Excellent. All right. So I'm going to put you on these. Okay. So Kai, find cosine of theta, please. Cheng, I'll have you find sine of theta. Cole, I'll have you find tangent theta. Let's see, Caleb, I'll have you find secant theta. And Nicholas, I'll have you find cosecant theta. And Jay, you can find cotangent of theta. So when you have it, just blurt it out to me. You can write it in chat, but just make sure I know which one you're trying to find. Okay, I think I have you on my screen. As long as nothing changes, I think we should be good. And the rest of you, see if you can't find these as well, okay? So you're going to be backups. So when you think you have it, blurt it out.
-6 square root 6 square root 2.
Okay, so 6 square root of 2 for cosine.
Now, how do you say this? -6,
Okay,
then
over.
over 6 square root 2.
Yeah, yeah. And how would you simplify that? What would that simplify to?
-1 square over square root 2.
Nice job, Kai. All right. Great.
All right. Secant is 6 radical 2 over -6.
Okay. And so that would simplify to
Radical 2 over -1.
uh-huh. radical 2 over -1, so it's going to be the reciprocal, and we'll simplify that to negative, that's a negative there, root 2. Sweet. Nice job, Caleb.
The secant is 6 over square root of 2.
Cosecant,
Cosecant 6 over square root of
6,
2.
6 over 6 square root of 2,
Yeah.
like that. Okay, so cosecant is going to be, let's see. That one's going to be,
Mhm.
yes, the that one's going to have the hypotenuse on the top.
Okay.
So it'll be the
Um,
reciprocal of
so
sine. I think
is-
you might have just helped us find sine.
Okay.
Yeah,
Um,
but is sine going to be positive or negative? And
Sine
that's
is-
the one that you were doing. You're right.
okay. Sine is going to be the positive.
Okay, so let's look at sine. I think I erased that negative there. So if we're -6, then I like to think of it as all students take. So the only one that should be positive here is tangent. So here we'd have a -6 over 6 root 2.
That's a -6.
There you go.
Mhm.
So it's going to be exactly the same as cosine. Nice job.
Cotangent is -6 over -6, which simplifies to 1.
Okay, cotangent is going to be 1. I agree. 2 more. Nice job.
Cosecant is negative radical 2.
Yep. So we just flip the script there. We take the reciprocal. And finally, tangent.
Just 1.
Yeah. So that one's going to be the reciprocal of 1. 1 over 1 is 1. So again, tangent, opposite over adjacent, those two are the exact same, so they cancel out and give us the 1. And then we can always write 1 as a fraction, or any whole number as a fraction is writing it over 1, right? So the reciprocal of 1 over 1 is 1 again. So those are the six values that we get out for the trig functions. So we remember, whatever we put into a trig function as an angle, whatever we get out is going to be a number. It's going to be like a ratio on a triangle or a number. And when we're taking those trig functions, they always have to be acting on an angle. Otherwise, they don't make sense. All right. How are we doing? Any questions? Okay. All right. Let's go ahead and look at our last section here. So I'm going to jump into 1.4. The last 8 minutes here. Hopefully I can do this. Okay, quit out of that. Sorry, it's being done now. Okay, here we go. Yeah. So I have some of these things in the book. I know you can't see it yet. But some of these things, when I'm teaching in Zoom, it's just easier to sort of copy some things out of the book and go through them. So that's what I'm going to do with you now. Section 1.4 is all based on identities, and more stuff that you'll have to think about when you're dealing with trig are manipulating things with identities. The good thing about identities is if you have one of the trig functions, they would enable you to get all the other ones. So they're sort of nice in that way. We're going to be proving identities later, but again, it's going to be step by step. We're going to be setting these up really sort of deliberately and hopefully build on each other. So the first ones we've already sort of talked about. They're the reciprocal identities. So essentially, if we're looking at, this is what we're looking at. We're looking at theta here, and our sides being maybe X, Y, and R. So the reciprocal identities, we already talked about if we have sine, cosine, and tangent, then if we take the reciprocals of sine, cosine, and tangent, we get cosecant, secant, and cotangent respectively. So those are defined that way just because of the definitions of the trig functions. So like, for instance, sine is going to be, sine of theta is y over r, but cosecant theta is defined to be r over y. So if I take the reciprocal of either one, I get the other one. There are identities called, so those are reciprocal. There's ones called ratio, and those deal with tangent and cotangent. So if you have sine and cosine, it'll be easy to find tangent by taking the ratio. And let's see how that sort of works out. So like we said, from that triangle, sine is y over r, and cosine is x over r. If I have two fractions and I'm dividing two fractions from algebra, might have been a while, but if I'm dividing two fractions or a fraction by another fraction, algebra says I can multiply by the reciprocal of the second one. And that's how we can cancel these things out. So I skip that first fraction, y over r. I flip the second one, take the reciprocal, r over x, and I multiply. The r's cancel out, and I get y over x. What is y over x? So TOA, it's tangent. So sine over cosine simplifies to tangent. Once I have tangent, I flip that around from the reciprocal identities, and I get cotangent. So cotangent would be cosine over sine. So those are the ratio identities.
Reciprocals are very convenient.
They are, aren't they? So some things in math are hard and some things are easy. We take solace and we praise those things that are easy, right? All right. And then finally, we have these Pythagorean identities. So the Pythagorean identities, you might think that they come from the Pythagorean theorem, and they really do. So if we think of these trig functions, and now we're going to be looking at the unit circle. So the unit circle is, unit means one. It's just a circle of radius 1. So the radius is equal to 1. It turns out if we have trig functions, that the sine and the cosine always lie in that unit circle. So if we have cosine being x and sine being y, then we can say, okay, cosine squared. So cosine in this case would be x over 1 squared plus sine squared. That's going to be opposite over the hypotenuse. Y over 1 squared is equal to 1. So that would be the radius, right? So the x plus the y squared is equal to the 1 squared. And that would give us cosine squared plus sine squared is equal to 1. This is probably one of the most important identities because we'll be looking at that throughout the course. When you're in calculus, it'll pop up. In your other math courses, that one will pop up quite a bit. It gives you a relationship between cosine and sine. So now if you have one, you can find the other one really easily. Okay, so there's two things I want to tell you about, and then we'll go through this last example. You can get those other two by just dividing through everything by cosine squared. So if I divide through by cosine squared over cosine squared is 1. Sine squared over cosine squared, it's tangent, but it's squared. And then 1 over cosine squared by the reciprocal identities is going to be a secant squared. So that's how we get this alternate one. If instead we divide this first one through by sine squared, then we get this other alternate formula. 1 plus cotangent squared is equal to cosecant squared. So these give us relationships between the other functions. Okay. Those are the important ones here. So I want to go through one last example, And then if you have any questions, you feel free to stick around. Otherwise, we'll have a good day. All right, so we want to find cosine of theta if sine of theta is equal to -1/4 and theta terminates in quadrant 3. So we could make a triangle and set this up and find all the sides and sides of this here. We wouldn't really worry about the angles too much. But we can actually use a Pythagorean theorem a Pythagorean identity to get that value of cosine theta. So I noticed that I have sine of theta. I want to find cosine of theta. So this is my relationship I'll use. This is the thing I want you to be really careful about. When it says cosine squared of theta like this, that might look nice. It might look aesthetic, but we're really not squaring cosine and then putting the angle on. We're actually doing cosine of theta. We're taking that value and then we're squaring it. So these are always equal. So I can actually just start out by writing it cosine theta squared plus sine theta squared. These are always the same, is equal to 1. So now I put in my value for a sine, and my sine is -1/4 squared. And I square that, that's going to be 1/16. So cosine squared plus 1/16 is 1. I'm going to subtract the 1/16 over. So I have cosine squared is equal to 1 minus 1/16. I have fractions, so I have to build them up to the same denominator. If I multiply by 16, I have 16/16. That's the same as 1, right? And then 16 minus 1 is 15. And I have the same denominator. And finally, since I have cosine squared, if I take the square root of both sides, I have cosine of theta is equal to the square root of 15/16. It's plus or minus. And you might see that 16 is a perfect square. So I can go ahead and replace that by 4. And do I use the plus or the minus in this case? So it terminates in quadrant 3. Is cosine plus or minus in that quadrant?
Negative.
Negative, great. All students take. Tangent's the only one that's positive. So my answer, great, to this one is going to be a minus. I can only get one answer out. And so in this case, it's minus, it's going to be minus root 15/4. Okay. So thank you for sticking around for a few extra minutes. If you still have questions, stick around. Otherwise, have a great weekend.